Morning. So I want to start talking about magnetic translation. So in the presence, so in B is equal to some, actually we have been taking like minus BZ, like a convenient sign. So this is like a uniform magnetic field, and at least on the classical level, and actually on the quantum level too, like there is like still translational symmetry in 2D plane. And what I want to show today is like when we generalize like Bloch theorem to the case with magnetic field, we'll not only learn actually a lot about Bloch theorem, right? It is going to like challenge our understanding of the Bloch theorem, but also it's going to give us some very useful tools. For example, we'll be able to understand Landau level degeneracy and then like spectrum, all these things in terms of symmetry without actually solving the Hamiltonian. So let me first remind you the translation symmetry in the presence of no magnetic fields. So if we don't have magnetic fields and if we have translational symmetry, what we say is like Hamiltonian commutes with, and so this can be vectors, but I will not write vectors unless I have to, right? In some context I need to indicate the vector structure, but not here. So if there is like a translation symmetry, that means Hamiltonian commutes with translation operator. And if you look at H psi is equal to E psi and act with TA here and act here with TA dagger TA and here put like a TA. What this says is like TA H TA dagger is H. That's exactly what this sentence is. Then H T times psi is equal to E times TA times psi. So what this sentence means, in the presence of like a translation symmetry, if psi is an eigenstate with energy E, and if we are assuming there's not there like energy levels are non-degenerate, in that case TA times psi is also an eigenstate with the same energy. Then if like this and this, these are the same Schrödinger equations, then these states should be the same. The way we say this is like psi is going to be equal to some lambda times psi. Let me actually insert arguments. So this is psi of x, which is equal to, by definition, psi of x plus a, and from this condition we require it to be like some complex number times psi of x, and typically this complex number is chosen to be e to the I k a. And to make sure that these are like labeled properly, we add the labels like that at the end. Okay. So if psi k is an eigenstate with E of k, T times psi k is also an eigenstate. So that's the essence of Bloch theorem. Now let's think about B is not equal to 0. And for the moment, let me just take V, like the external potential is 0, and I'm going to also include external potential towards the end. Hamiltonian is H 1 over 2m P plus E over C A of R squared. And A defines uniform magnetic field del cross A of R is equal to B, which is uniform B perpendicular to 2D plane. Now I want to do exactly the same thing here. So the h psi, let me just copy this. So this is h psi is equal to e psi. So what we did was like hit with t. Did I use? Let me use ta from the left hand side and insert here ta dagger ta, and here so this identity is 1, and here this is ta, and we look at the Hamiltonian. So this piece is equal to 1 over 2m. So we did exercise like this. Let me just write the result. If you don't know it, please sit down and try to convince yourself why this is the case. This will give us p is going to go to p plus e over c. A is going to go to a r plus a squared, right? The only r dependent quantity is a, and I shifted it by the translation operator. And I will define this to be h prime. And now coming back to uniform B. Uniform B means del cross A of R is, let me write B of R, but we have to keep in mind B is uniform. And if I, wherever I see R, I can just write B of R plus A. So this one I'm going to shift plus A, and this is B R plus A, but B of R is equal to R plus A is B of R. That's the meaning of constant magnetic field. That means A of R and A of R plus A are related by like a gauge transformation. How? If I have A of R plus A is equal to A of R plus like some gradient which may depend on A, because curl of gradient is 0, this quantity is automatically del cross A, and B of R is automatically equal to B of R plus A, right? And this is like what we called gauge transformation. So H prime here and H are related by like a gauge transformation, and we are trying to figure that out. Now let's also consider, for a general function e to the I phi of R, H prime e to the minus I phi of R. I think we also did something like that. In that case, phi of R is only going to be affected by P, right? And it's going to bring down, let me write that, 1 over 2m. This is P minus I h bar, and from the gradient we are going to bring down a minus I gradient of phi, and there is also, okay, let me open up some space here. So this is that, and I also need to put plus E over C A of R, and also the second piece, which is this one, plus E over C, this gradient of a function f of A of R squared. So this, okay, I think I can fit it in one line to see it better. And minus I and I, what did I get there? Here, right? This is going to be let me erase this one and put like a minus sign here. And in that case, I want to choose such a phi of r that this new equation is going to be equal to h. In that case, I'm going to find the exact gauge transformation which brings back to original Hamiltonian. For this to happen, h bar del phi should be, so this piece and this piece, if they cancel each other, I'm back to original Hamiltonian, and for this to happen, I'm going to have e to the e over c gradient f a of r. Let me write then, so we can integrate both sides and write phi. Actually, I'll also add this label a, phi of r is going to be equal to e over h bar c f a of r. E over h bar, okay, this is correct. Let me box in, I'll use this later. In that case, so the message is if we combine e to the I phi a of r and t a into a new translation operator, which I'll call it like ta tilde, then in that case I have h commutes with ta, right? And now I have a translation operator which is decorated, that has the same form as in the Bloch theorem. Good. Then does this mean that I can automatically use Bloch theorem? Do I need to check anything else? Is this the end of calculation? If I now see this, so initially what we had is when b was non-zero, h and t were not commuting because there was like a shift, and this shift was related to a gauge transformation. But now with this additional phase, it seems like I have like a t tilde which commutes with Hamiltonian. Now can I just immediately run to apply to Bloch theorem, or is there anything else I need to check? So this is one of the tricky questions that we have to be aware. So this is not enough, this not sufficient yet. So what we also need to show is like if we have two operators, ta1 and ta2 for two translation operators, we also need them to commute, right? If they don't commute, that means we have like two different operators that commute with Hamiltonian, but these two operators do not commute with each other, and that's not assumed in the Bloch theorem. In the Bloch theorem, they are also commuting. So let's check if that's happening. So this is needed. So then let's write this. Let me write this like it's a little bit easier to write a and b. Let me write it a and b, and also it's easier to read in that form. So what I want to calculate is like t tilde a, t tilde b minus t tilde b, t tilde a. So I want this thing to be 0. And let's write the, let's unpack. So this is e to the I phi a ta. There's like r argument, but I'm not writing. Like the important arguments are written, but the others are not. So this is e to the I phi b tb minus, so this thing. Like that. Now I want to insert here T A dagger T A, and I want to insert here T B dagger T B, and I want to identify this vector. So what is this thing? So this thing, let me just write it separately here. TA acting on a function, like here phi b depends on, let me write it. So this is phi b depends on r, and phi a depends on r. So this one depends on r, and this one depends on r. So what is the result of this operation? TA, a function of r, TA dagger. What's that?
R plus A.
Exactly. So this is going to be e to the I phi b r plus a. So this is shifted. Similarly, this one, right? I have this thing. So this is e to the I phi a, and the shifted one is r, and shift amount is b. Good, a little bit seems tedious, but like if you are careful, not really. So then this is e to the I phi a of r, and plus I phi b of r plus a, and now I have what is left is like TA and TB. So this is TA TB minus e to the I phi b of r plus I phi a of, so this is AB BA, okay, good, r plus b, and this is TB, and then lastly TA. And TA, TB, okay, let me write one more line. So TA, TB is equal to TB, TA is equal to TA, TB. They commute, they are the usual translation operators. And if we require this to be 0, I can cancel these out. So let me cancel this one and this one. In that case, this quantity should be equal to this quantity, so that these two translation operators do what we want them to do. So in that case, what we need is, let me write it here. So this thing should be equal to this thing, or these exponents, like this thing minus this thing should be what? So this is, what's that? Exactly, this is 2 pi. Let me write like a big N, but this N is nothing to do with all the other N's.
That should be also another minus.
Oh yes, yes, thank you, absolutely, good job, yes. Now we need to like play with this a little bit to see something physical out of this. Like these are like at the moment are not something we can relate to. So let me remind you, this A of R plus A is like a gauge transformation. What this means is A of R plus gradient F A of R. Or we can write this in the alternative form. This del F A of this thing is equal to this minus this. I just rearranged. And I can then integrate both sides, right? I can write it like f a of r is equal to, right? If I take out a derivative here, I need to take out a derivative here, and taking out a derivative here is like integral, and okay, so this is, let me write it like dr prime a of, so this is line integral r prime, and it goes from r to r plus a, right? Something like that. But we said this one here above, if you remember, let me just show you. We said this thing, if you multiply with e h bar over c, is equal to this phi of a. So this is, if you multiply e, was it, over h bar c. Actually, let me write let me write it like this. I will write e over h bar c here. This is going to be give me, yes, phi of a. So okay, then this is phi of a. Good.
Can you explain this integral form also?
So this line. So I rearrange. So going from this line to this line is okay, right? And this line, if you want, I am just taking the. If you take the derivative of both sides with respect to r, you get this line.
Okay.
Right? Yeah, exactly. You need to just take care of the boundaries. Then I want to write this. There are like 4 terms here. I want to write them like an integral in terms of this vector potential. So then this is going to be the first one, e h bar c. So this is phi of r is going to be from r to r plus a. So this is the r prime dotted a of r prime. So this is the first one. Plus there is like a similar one. I'll just change the limits of integral. This is the second one, and the second one is going from r. What did I write here?
Does an integral hold with down?
This integral?
Yeah, doesn't hold because you have a in the integral and you get the a's.
Like a big A in the integral, yes, right? If you take the derivative of both sides, this is supposed to give you this line, right? And the only thing that comes out is the boundary term.
The left side is the same sign as the above one with the down. There's no yeah, in second division.
Oh yes. Yes. Sorry, I think I wrote it to show. Yes, thank you. Good job. Yeah. So this one is going to go from r plus. So this is going from r to r plus a to r plus a plus b, r plus a to r plus a plus b. So the next one is okay, the same thing. So this one is going to be minus, and this is going from r to r plus b. So this is r to r plus b. And one last one. So this is going to go from r plus b to r plus b plus a. B plus a. Now I can just look at this line. But let's see what this thing is. I have like a position. Let me just call it like this is r. And I go from r to r plus a. Let me just choose. So this is my, let's say, r plus a. So this one is like that. Now I go from r plus a to r plus a plus b, and r plus a plus b is this vector. So this is r plus a plus b. So this one is taken care of. This one is going from r to r plus b, but with this minus sign I can convert the integral, and I will go from actually let's go look at this one first. So if I change the limits of integral. This is going to go from r plus b plus a to r plus b, which is going to be something like that. So this is r plus b, and so I've taken care of this. And last one is going to go from r plus b to r, something like that, right? Hopefully, and so this is just the line integral of a around this plaquette. And if I have like a face, let me just call it like phi, this parallelogram here. This is basically just Aharonov-Bohm face. Like an Aharonov-Bohm face, the most physical thing we like. Then this quantity, this thing is equal to E over h bar c phi plaquette, and this is going to be phi plaquette. So h bar, I'll write it like 2 pi, and hc over E is flux quantum, so this is phi naught, and we said we require this to be 2 pi n. Then the conclusion is, if flux over flux quantum is integer, then Ta tilde and Tb tilde commute. And now there is nothing else. Once you show that, you can apply Bloch theorem and you are done. Bloch theorem applies. So let's consider a couple of cases. First, the most trivial case, if A is parallel to B, in that case, right, there is no flux, there is no plaquette, because the area of the plaquette is 0. In that case, n is going to be 0, and Ta tilde and Tb tilde commute trivially. And so if Bloch theorem applies, let's also write that. If Bloch theorem applies, you can write functions like k of r, like e to the I k dot r, some un k of r. So the periodicity of un is a little bit also different. I will also show this in a little bit, but this condition defines k, right, the Brillouin zone, and in that case k becomes 1D, which is like Landau levels, Landau gauge, which we have been studying a lot. But the more interesting one is let's to get to the Brillouin zone, A should not A and B should be not parallel. I don't know what else to say with that. And the minimum condition here, the minimum phi over phi naught. What is the minimum flux you can trap? It's supposed to be integer, and the minimum integer is just 1, and this is the primitive unit cell. And right, like if one flux is one primitive unit cell, total flux is total system, then number of cells is equal to number of states. That's what we also used in the case of Bloch theorem. However many sites you have is the number of states. And then from here, the cell number is this n phi, which is total phi or phi naught is lambda level degeneracy. So right now we still didn't get the degeneracy, but like the number of states in a given lambda level is given by this n pi from this argument. Let's also see if we can understand degeneracy. So here's the placket we wrote above. So this is the placket. And so B is constant inside. But if I continuously deform this placket in such a way that area is conserved, right? Maybe I can just open up something like that. Maybe I can do something like that. It doesn't matter as long as the area is conserved. So nothing changes. And so A's and B's are primitive lattice vectors of the real space. Continuous change of A and B will result in continuous change in Brillouin zone. Right? If you change the real space, you change the reciprocal space. Right? That's why like square lattice has a square Brillouin zone. Honeycomb has like honeycomb Brillouin zone and so on. Right? But the vectors A and B are arbitrary here, and choose like continuously deforming these A and B should not change physical results, and this means E n of k should not change. With A and B. And we also know E n of k is going to be periodic. What is the only function that's both periodic and does not change with continuous deformations? What is there's only one function that doesn't change if you change case. Exponential?
Imaginary.
Simpler than that. What is the simplest non-trivial function? Constant, right? So if E n of k is constant, what this means is k independent, then it is not going to change. And that's exactly the case. If you remember, we had h bar omega n plus a half lambda level energies, and these lambda level energies doesn't know about k, and that actually comes from our argument without any gauge choice. And also their degeneracy from here, right? One unit cell is one quantum flux. Total number of unit cells is number of fluxes. Then there is like a constant energy level, and their degeneracy is n phi fold degenerate. So lastly, I want to close with taking like, let's assume also B is non-zero but still uniform, but V of R, let's also take a periodic potential. And I'll take a break after that. In that case, we need to consider H is equal to 1 over 2m P plus E over C A of R squared plus V of R. And here we are assuming, so this V of R is equal to V of R plus, I don't know, let me call this C. There's some other periodicity related to, right? Like the lattice potential and the vector potential, they have nothing to do with each other. So this is going to have like its own periodicity, and A is going to have its own dependence, and we are going to deal with them like this. Then we want to have the following. So we want to have T tilde Let me now call it A1 and T tilde A2. So need, because we are in 2D, I need at least two of these, need such that they should commute with H, first of all. H and T tilde A's should commute, and they should also commute with them, each other. So this one and this one, if A1 and A2 are different. So this second one is by construction satisfied, but now we have to think about this because we have like a new term in the Hamiltonian. So for this to happen, we need to have V of R plus A1 should be equal to V of R plus A2, and this should be equal to V of R. So A1 and A2 are lattice vectors, but not necessarily primitive, right? So now let me just draw you a picture to show you what this means.
Was that
Uh-huh.
the elliptic functions? Like,
So we'll come to elliptic functions in a little bit. At the moment, we are just like playing with the symmetry. Eventually, they will be, yes. So here's let's say this is A. So this one is B. Let me translate this one like this and this one like that. So this one is A1, this one is A2. And this is the periodicity of like magnetic Boolean zone, right? Magnetic unit cell. But for this to happen, the only way this can happen is like maybe we can also have like these little unit cells here, where V is periodic. Let me not write so many so that I can write it a little bit quicker, like this. So this red line. So red line is unit cell of V of R. So the blue line is unit cell of A of R, which we have been like trying to formulate the whole time. And when we see this, this will be satisfied if if flux in the placket. So if flux is equal to P, let me write, if we have P flux and Q red plackets, this one is going to be satisfied, right? Where P and Q are mutually prime. What we are trying to say is like, I mean, if you go to the unit cell of V of R, you may not come back to yourself under A, but if you repeat that translation, I don't know, some like Q times, you'll come back to yourself. But when you do that, you are going to bring P fluxes. So that's the condition. Any questions? Maybe I can stop here and continue with Bloch functions in the second hour.